Let's take a look at Module 7 Novice Problem Solution number 2 now. Again, we're doing linear programming. And recall that linear programming is a decision-making model that tries to optimize either by minimization or maximization. So optimize is a very general term for either one or the other. Some problem where we have decision variables and we create an objective function and constraints that limit the possible values of the decision variables that we can use in making a calculation of the objective function. So let's get out of this and go to our problem set. Here is the problem we're looking at. This is the problem related to a graphical solution. The book spends some time on graphical solutions because they make a very good sense in what's going on in a linear program. Of course, graphical solutions are only of any value when the number of dimensions that we have are well understood by our puny little brains. And 2 dimensions is what we do best. We can think in terms of 3 dimensions. That's more difficult. In terms of 4 dimensions, you know, you're on the planet Xenon at that point. So we have a problem that has 2 variables, x's and y's, and we've got some constraints. X is greater than or equal to 2, x is less than or equal to 6, y is less than or equal to 9, and then a combined set of values of x and y that give us a linear function that has a slope. In this particular case, a negative slope. Why? Well, because if we take the x and move it to the right-hand side of this inequality, this becomes a negative, and that, you remember from your algebra, y is equal to mx plus b. b is this constant. M is the 1.5 in front of the x, and in this particular case, since it's going to the right-hand side, we have to subtract it from both sides. It'll be a negative. So first we ask, which constraints form the shape x? Let's see what the shapes are that we're looking at here. So we've got 3 different shapes. Here is x, here is y, and here is z. I'll take that out of there. I know what that was doing there. So if we look at this particular shape, we see that we've got kind of a rectangle and then kind of a triangle that sits on top of that. So how do we get that? That's a right triangle. It looks like our constraints are shown here on the graph. This constraint is x is greater than or equal to 2. This constraint is x is less than or equal to 6. If we go back to our constraint set, y is greater than or equal to 9 is, that's y is less than or equal to 9 is this constraint here, and all the area underneath it, of course. And we need to, since these are inequalities, we need to know the sense of the inequality. This is x is greater than or equal to 2. This is x is less than or equal to 6. Everything on this side of the line, everything on this side of this line. So this shape obviously fits this rectangular area here and then this triangle on top. And so x is formed by constraints 1, 2, and 4. And so how do I know it's 1, 2, and 4? Well, if we go back to the graph, 1 is equal to the constraint 1 is x is less than or equal to 2, greater than or equal to 2. So this line, and this line are those constraints, 1, 2, and 4. So which constraints above form the shape Y? Here is the shape Y, and this looks like a little a triangle. And if we look for the constraints that form this triangle, the only place where we can find it, that particular shape, is in this area here. So it will include this constraint, which is y is less than or equal to 9. It will include this constraint, which is x is less than or equal to 6. And then, so we've got this constraint, and then this constraint, which is the constraint that 1.5x plus y is less than or equal to 12. So we've got 2, 3, and 4. 2, 3, and 4. Which of the constraints form the shape Z? If we look at Z, we see a rectangle, and the constraints of interest are here, here, and here. So, of course, this constraint does not enter into the formation of this region. So we've got y is less than or equal to 9. We've got x is greater than or equal to 2, this area in this direction, and we've got x is less than or equal to 6, which form that. So this constraint, and this constraint. And those constraints are 1, 2, and 3. 1, 2, and 3. Which of the shapes describes the feasible region for our linear program? The feasible region of our linear program is the combination of all 4 constraints and the area that is applicable to all those 4 constraints. In other words, an area that includes all of the constraints. And we can see from our graph that the feasible region is formed by this area here. We don't include this because this line, this constraint says everything below here. We include this one because it says everything to the right, but it stops here. We include this one because everything to the left, and it stops here. So our feasible region is this region here, x, and those are the values that do not violate any of the constraints. What is it, how do we maximize the objective function? We know from our linear graphics that the corner points of the feasible region, this point, this point, this point, and this point, these are corner points where you have a distinct corner. There, there, and there, 1, 2, 3, and 4. Those are the candidates for the optimal of the objective function. And all we simply have to do is take this point, this is x equals 2 and y is equal to 0, stick it into our objective function, calculate it, do that for x equals 6, y is equal to 0, for x equals 6 and y is equal to 3, and x equal 2 and y is equal to 9. And for those 4 distinct corner points, calculate the value of the objective function, and the largest, of course, will be the one that maximizes the objective function. In this case, y is equal to 2, or x is equal to 2 and y is equal to 9, gives us an outcome of 11. If we had used 6, x is equal to 6 and y is equal to 3, 6 and 3, we get 9. Of course, that's less than 11. And of course, these other 2 corner points down here are going to give us very small values for our objective function. So the objective function is maximized at this particular point. That's the end of problem 2, module 7.